Okay, hello everyone. We are here to do a kind of science meets technology discussion about gravitation, general relativity, Wolfram model, hypergraphs, and related topics. And we're going to talk about some of Jonathan's work on developing function repository entries and so on for doing general relativity calculations basically on the basis of hypergraph rewriting and so on. And I guess if we're lucky, we will manage to segue into some discussion about actual practical astrophysical experimental implications of our models. Okay, so Jonathan, let's sort of aim for, I want to simulate the collision of two black holes.
Right.
Where do I start?
Okay, so first thing to know is, the sort of the first class object in this whole framework is metric tensor, right? So pretty much every other object that you and every other function that you would call in the GR framework has at least one metric tensor object attached to it somehow. So metric tensor, if you pull up the details, you'll see that metric tensor has a bunch of inbuilt metrics already available, and we have plans to expand that library. Hopefully it'll become like a sort of axiomatic theory type function where.
Okay, so hold on, where is this now?
So if you look at the details section of the documentation, then somewhere there. Okay, yeah. So that's a table of all the inbuilt metric tensors that we currently support.
Okay, so let's take a Kerr with a mass.
Right.
So how do I then get?
So if you just call metric tensor, if you just call metric tensor and then and Kerr, it will do the general case of Kerr.
Okay. Look at this new tech.
Metric tensor.
Oops, very bad. Well, it's going to fail there. Okay, what is this?
So that's now a symbolic metric tensor object. So you can see by default, it's in covariant form. So both of its indices are lowered. And so you can look at its matrix representation if you just take that thing and you call and you request property matrix representation.
Okay. Pity there's no autocomplete for that.
That can be.
What the heck happened here with this metric tensor turning blue?
That I don't know. That I don't think that should happen.
Well, it's happening because you've named a symbol and it's not in the system context there.
But except it shouldn't be that should be a string name.
Because this whole object should be a resource function. Is that correct?
Well, so the summary box is not like the summary box should not have symbolic metric tensors. It does not have symbolic metric tensors as its first argument. It has string metric tensors as its first argument.
Okay, I don't understand that. Jose, do you happen to know how that works, or Nick?
No, I don't know.
Okay. So that's
okay.
Aubrey, can you make a note of that so we follow up on that?
Yep, got it.
The reason for that is, so if you have a function repository entry that returns just like a summary box with the symbolic name in it, then it renders really uglily because its context, it will have some random context.
Yeah, sure.
So to get around that, the WFR team said that the correct thing to do is just have the string name in the summary box rather than.
Well, okay, but so somehow the summary box is breaking itself open. That's a separate issue. Okay, so we've got a Kerr metric, and so now what can I do with this?
Okay, so if you look at the full properties of metric tensor, you can see the things you can do to it directly. But mostly this is just different ways of visualizing and computing simple thing. You can look at this. You can look at the space-time line element, or you could you can extract out pure functions that allow you to.
Where's the space-time?
I think it's just called
Line
line element. I mean, because in principle, this doesn't have to be a space-time. This could just be an arbitrary metric, right?
Why does it say ds squared equals, as opposed to just this being the line element?
I mean, it could just it could have the ds squared be implicit if you prefer.
Well, I just think then it's an equation here. This is not a line element. This is an equation.
I know, but you know, I don't know. Usually, if you see someone say this is the line element for Kerr in a paper or something, like that's what they mean. Like,
or maybe it should say line element definition or something, as opposed to just line element, which I really think should just be the actual thing.
I think. What do you think?
Jose, are you with us?
Sorry. Yes, I agree with Stephen. It would be more computable to have something that is one of the sides of this equation.
Okay, fair enough. I mean, for what it's worth, the computable form of the line element would be length pure function.
I see.
The line element is supposed to be a kind of symbolic thing.
Where does that? Sorry, you have.
So yeah, length pure. It's the last but 3 or whatever of the properties. So now, if you take that and you apply it to a 4 vector, it will give you the length of that 4 vector in Kerr.
Euclidean 4 vector. I mean, the Minkowski 4 vector. What kind of a?
Well, yeah, a 4 vector with minus plus 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 signature. There you go.
What's theta?
Sorry?
What's theta?
Oh, theta is the angular coordinate. So.
Oh, I see. Because it varies with the position. It's not. It's
exactly.
Not
yeah.
It varies with the radius and the position.
Yeah, precisely.
But it has only a cylindrical. It has cylindrical symmetry of some kind, so it doesn't have a phi. Precisely.
And similarly, if you did angle pure function, that would give you a 2-argument pure function that would allow you to compute the angle between 2 4 vectors.
Okay.
So this is the length of a vector at the tangent space at that point.
Yes.
Right. Okay. So one issue here, I mean, so the question of how to make a lightweight repository is an interesting question, because that's what we really need for this. Although, what about these parameterized ones? How do they work in a repository? Do we have that issue with axiomatic theory?
Well, we do, because we allow for operator renaming, don't we?
Oh, that's right. So it then becomes an association.
Yeah, I mean, that was in the original design. That was why we decided against having it be. I think the original plan was to have axiomatic theory be an entity store, and the reason we decided against that was because we couldn't find a nice way of doing the operator overloading.
This feels similar to coordinate chart data, and we have the same issue there with parameters.
Well, I mean, it's possible this should actually be promoted one day to an actual system function of some kind. It's kind of weird here that, I mean, these are some very standardized set of coordinate systems, aren't they? Like there's some number of curvilinear coordinate systems, and we have all of them. Is that a fair statement?
Yes. So yes, these are the orthogonal.
As opposed to know what that means. Why does that? How do I get the analog of the metric? Oh, I can actually just ask for the metric. Okay, so in that case, the metric is a function.
Yes, if you provide a third argument with coordinates, list x, y, z.
Okay. Let's see, if I say, okay, but toroidal coordinates, for example, I have to give a parameter here. Aubrey, please report. This is 13.3, and it's pinking. It's this suggestions bar.
Got it captured. I'll report it.
What the heck? What's the R doing here? I think toroidal A. What's this?
I don't know, to be honest. I can follow up on that.
What's going on here? Okay. Well, in any case, so this is a model. What is the relationship between coordinate charts? I mean, in general relativity, there are often multiple charts characterizing a given metric. Is that not true?
Yes, and so okay, and this is okay. This is a genuine design question. So right now, to make this a little bit concrete, right? If you say metric tensor Schwarzschild or something, by default it will give you the Schwarzschild metric in Schwarzschild coordinates.
Okay.
But you can also say something like metric tensor isotropic Schwarzschild, and it will give you the Schwarzschild metric in isotropic coordinates. Or you can say, what else do we?
Eddington-Finkelstein coordinates.
Yeah, exactly. So you could say Eddington-Finkelstein if you wanted to, and it will give you
where
the
and how. So okay, so this is I can ask for Eddington-Finkelstein, which is not just a metric, but it's also a coordinate system for the metric. Is that correct?
Right, and so by default, that gives you the Schwarzschild metric in Eddington-Finkelstein coordinates. So it's okay. On the one hand, there's something a little bit uncomfortable about treating these matrix representation. There's something a little bit uncomfortable about treating these things as separate metric tensors when they are like as you say, different coordinate charts for the same geometry. My reason for having them be separate be treated as separate metric tensors is because they are, in some sense, different manifolds, right? There are bits of the, like, if you were to plot the isotropic Schwarzschild metric and you were to plot the the Eddington-Finkelstein version of the Schwarzschild metric, and you were to plot the Schwarzschild coordinates version of the Schwarzschild metric, they don't look the same. On the interior, they have different geometries. And so my feeling was it makes, even though they are just different coordinate charts, it makes sense to treat them as different metrics.
But wait a minute. Physically, if you could penetrate the event horizon, would they be in fact different?
Well, I don't think that's a really meaningful question, right? Because the Schwarzschild coordinates only apply to an observer who is infinitely far away from the black hole or from the mass distribution.
So in other words, what you're saying is, it's kind of like an interpolating function where in the region where the thing is supposed to be valid, they agree.
Right.
And then it goes bonkers elsewhere.
Right. I mean, an extreme version of that is Kruskal. We support the Kruskal-Sekharez metric, right? Which is, Kruskal-Sekharez, the Kruskal extension of the Schwarzschild metric. And so again, that's a very evocative example of where they are both defined, it agrees with the traditional Schwarzschild metric and Schwarzschild coordinates. But there are many bits where Schwarzschild is not defined, but where it is defined in Kruskal-Sekharez.
What's this ±1 doing?
So that's because you can have both ingoing and outgoing Eddington-Finkelstein coordinates. So if you say ingoing Eddington-Finkelstein, that will change to just be a plus. If you change it to outgoing Eddington-Finkelstein, it will change it to just be a minus.
Okay.
We have the same thing with things like ingoing and outgoing Gauss-Strand-Panleve coordinates and so on.
It's showing me what I should be doing for this toroidal thing. Oh, wow. So what does the Euclidean mean there? And how does that relate to what we're doing? What is the role of Euclidean there?
So we have metrics that could live on the sphere or different dimensions, etc. So this is a case in which there are other possibilities. I have to check with Itai, and it seems that we need a full specification in this case.
But this notion of Euclidean here, in a sense, for all of these, we could have said Minkowski, in addition to the, I'm confused. So coordinate chart data as compared to Eddington-Finkelstein here. That's the same type of thing. Toroidal versus Eddington-Finkelstein is
So,
this is
so,
very confusing. This is a
so-
labeling. Eddington-Finkelstein is a labeling of the Schwarzschild manifold, so to speak.
so there are two different things here. So in the coordinate chart data case, we support coordinates for the sphere and for the flat space, with the Euclidean
Okay.
space in any dimension. In relativity, the coordinates and the space are so the metric and the space are mixed. And so it's a bit less clean in the general relativity case. I think we have to say sphere. And
Well,
and
it's auto-completing to spherical, so I don't know why.
I see.
It auto-completed to spherical, but maybe it doesn't support.
So not all coordinate systems are supported for the sphere, of course, but
Right, a toroidal is pretty weird on the sphere. There's some weird homotopy thingy going on there.
right. So again,
What would I could try polar, for example, here.
Hmm.
I'm confused. Okay,
So
but-
for example, we have stereographic for the sphere as well. Sphere, change to a sphere.
even though the autocompleter says spherical, which we need to look at.
Yeah.
Okay. All right. So say again what you were saying about the fact that because one could expect somewhere here, and Jonathan's probably going to explain, that there could be a base here of four-dimensional Minkowski space. It's basically the thing.
But the problem is, okay, and I guess when you say the basis in four-dimensional Minkowski space, I guess you mean we're just treating this as a minus plus 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 manifold.
Right.
So
A luxury that we do not have in the hypergraph case.
Or really in the relativity case, if we're being honest, right? Like, if you take one of these metrics, you can say, for instance, Lorentzian conditions, and it will tell you what conditions on the coordinates are needed in order to guarantee that that happens. But like, if you pass R equals 2m in the Schwarzschild geometry, then it's no longer Lorentzian.
What does that mean?
Okay, so that means that there's no coordinates. There are no ranges of coordinates in which that is truly Lorentzian.
How can that be? I don't understand that.
You might, okay, hang on. We can maybe look at that in a sec. But okay, if you look at the Schwarzschild case, those are the coordinate conditions you'd need.
Right. Those first two conditions are the same.
Yes. It hasn't reduced those out. You can say reduce on that, but
Okay. And how could this not be true?
well, I mean, in principle, there's nothing
greater
to
than
stop.
0. Is there a theta equals 0 case?
Yes, and the metric does become singular there.
Huh. Okay, so
coming back for a moment to the structure of coordinate chart data, so that's trying to separate the geometry from the coordinates in which that geometry is being expressed. So in relativity, we could.
But why didn't this work?
It probably would have done if you didn't have complete. So the symbol, all the coordinate symbols are maximally formalized. If you change the second argument of Schwarzschild and just make it be and have that argument be a list, say TR A1 A2 or something.
Why should it care that they're formalized here? I mean, I don't understand why it makes any difference. It's just they're just symbols. Why does reduce care?
If you try it with non-formalized symbols. I don't know. That's
Okay, what do you think that's the condition? Well, how many variables are there here?
4. Oh, and you might need to change. Oh, sorry. Try that. Okay. You may also need to say in Schwarzschild, change that to a list of Schwarzschild, comma something for the mass. There we go.
That's just bizarre. What the heck? Why does it care?
I mean, and
does it think it needs to go inside? Those are formal symbols, right? So that if I look at the input form,
they might actually. I think they're stringified formal symbols, which is even
yuckity.
I had my reasons.
Why the heck do they have to be stringified? Well, that's going to break a lot of things. So that's highly undesirable that they're stringified. So it'd be nice to not have
they're
that.
only stringified in the way that they get presented. They're not stringified in the interstices of the function. All the computations are done on non-stringified versions.
Okay, but fine. But when they come out like this, we got to be able to evaluate them.
Right. I mean, I can have them return a non-stringified form. Yeah.
Seems highly desirable. Okay, in any case. All right. So where do we go from? Okay. So these metrics are named metrics.
Uh-huh.
And just so I'm trying to understand, in the modern world of machine learning for everything and LLMs and all that kind of thing, I can make a reasonable picture of a rabbit in 3D by just using some text prompt. Is it conceivable that I could create a general relativity metric from a text prompt?
An analytical one?
No, probably not. I mean, just like I can say, if I say 3 black holes in gravitationally bound, this is going to be unbelievably scary and ridiculous. But
I doubt it. I mean, I don't know enough about LLMs, but
I mean, this is somewhat ridiculous, but
it's cool.
It's cool and amusing. But my point is, what people are going to want is an easy way to create initial conditions for things.
Yes. Yes. That much I agree with. And so, I mean, if we want to talk about initial conditions, we probably need to talk about ADM decomposition, which is the function that really does that.
All right. But this is generating analytical metric tensors and things.
Exactly. So if you want to do an initial condition would be a metric tensor object, but it would be a 3-dimensional rather than a 4-dimensional. It would have 1 dimension.
Yeah, I get it. For time. Okay, but so just so let's say I'm trying to invent a great new solution to the Einstein equations. Right. Actually, for each one of these, presumably there's an energy momentum tensor that goes with it.
Right. Okay. So if you take one of these metrics that you happen to have used only vacuum metrics, right? So that's pretty easy. We can just take one of those metric tensors. You can say, you can call resource function solve vacuum Einstein equations on any of these.
On the metric tensor.
On the metric tensor, and then you probably want to say you probably want to say comma 0 to say that you want 0 cosmological constant. Otherwise, it will assume non-zero cosmological constant, and then it won't work. Okay, so it's telling you that is an exact solution to the field equations.
How do I tell that from this?
It says exact solution true.
I don't understand this output. I mean, normally I would expect. I'm a bit confused here. So this is saying this thing. So for example, let's say I put in the
so it's arguable that this thing should not be called solve. It should be called reduce or something. So what it's doing is you give it a metric tensor object. It will determine does this just directly solve the Einstein, the Einstein equations exactly? And if not, are there conditions we could use, or that we could impose that would mean that it does? Okay, yeah. So in that case, if you get rid of the 0, there we go. Okay, so it's a solution, but it assumes 4 field equations. So if you extract out field equations from that,
Can you, for example, compute the Einstein tensor?
yes.
For given metric?
Yeah. So if you call resource function Einstein tensor on a metric tensor, then you can compute. Yeah.
Because then using the Einstein equations, you could say this is equal modulo of constant to T mu nu.
Yeah.
Right. Exactly. Which is what solve Einstein equations does in generality. So yeah, if you take the Einstein tensor, if you say, so you can call that and say, reduced matrix representation or something, that will show you the matrix representation of that tensor with all sort of known algebraic equivalences imposed.
Reduced matrix what? Representation?
Reduced matrix representation. Just like, so you can call matrix representation or you can call reduced matrix representation, depending on whether you want it to be auto-simplified or not. So that's the Einstein tensor for the Gödel metric. And then you can set that equal to something, right? So you can say stress energy tensor. Oh, okay. So that should return a 0 matrix. Schwarzschild has a W.
Yeah, so it does. Lovely. Okay, so what about something with, so this has a big cosmological term play. But what about?
Well, actually, so the Gödel metric is really it's a dust metric, naturally. Okay. So if you say resource function stress energy tensor, okay, so we have a bunch of inbuilt. We have a small library of inbuilt stress. Okay, that's not going to work. You need to give it. So first of all, the first argument, you need to give it an actual stress energy distribution. That could be, for the Gödel case, you probably want it to be dust or something.
This is too complicated. I think I get the point, but let's not get pulled into this hole here. I think I'm understanding. What we're looking at roughly is we've got, a bunch of name metrics, but now if we ask the question of all, and you were now talking about the ADM decomposition, but as far as the for all time metrics, which is what these are, aren't they?
Yes.
So just a sort of a learning moment. What for all time metrics? Aren't there like, I don't know, Bianchi type something or other universes and things that represent sort of with given symmetry for all time metrics, or am I not right about that?
I think so. If what you're talking about is, you can certainly parameterize like classes of metrics. The Bianchi universes are one such parameterization.
Right. Is there a place where somebody has like collected endless sort of exact solutions?
I know there are books that have tried to collate these things, but I don't know if Jose has information.
Yes, those books are the main references. Some people have tried to collect them computationally, but well, there's not an accessible database where you can go.
Well, you mean they've tried to collect them but haven't succeeded, or they've tried to collect them and they keep them to themselves, or what's the?
They are adapted to some. Because there are multiple packages for tensor computations, they are collections adapted to one of these packages.
So, like for exact, is there a collection?
We don't have an exact. We have notebooks with examples, with collections of examples, but we don't have a systematic collection of metrics. It has been proposed, but nobody did it so far.
Well, is there something that we could get? Is there is this a project for somebody to go and try and collect? And then how many are there? Are there like 500? Are there 200? How many are there roughly?
There are
And how
families.
funky are the stress energy tensors? Go ahead.
They can be very strange, and sometimes they are classified by algebraic properties. So it's not that they correspond always to physical scenarios.
Mm-hmm. Okay, but so for example, I mean, like the failure of a solution to the helium atom in analytical form, I suspect for more than one black hole, you're out of luck for anything analytical. Is that a true statement?
Certainly no analytical solution is known, yeah. And it's widely believed that they don't exist.
Mm-hmm.
Well,
I don't think anyone's ever proved
functions.
that.
The 21st century class of special functions, yes.
Right.
I mean,
yeah,
unless it's undecidability, it's either going to hit the wall of undecidability, or there's going to be a 22nd century set of of special functions.
But so certainly in ADM decomposition, you can produce a symbolic metric tensor that corresponds to a black hole to a binary black hole collision. But it involves things that you need to determine essentially by numerical differentiation, by doing numerical integration.
All right. So if I go here to ADM decomposition, I'm going to start seeing.
Yeah. So if you go in here again, we have a subset of the of the things in metric tensor as sort of initial condition libraries. So if you say ADM decomposition Schwarzschild or something, you don't get the same Schwarzschild metric that you would have got from metric tensor. You get a sort of more underdetermined version of it, where you only know the Schwarzschild geometry on the initial space-like hypersurface.
Yes.
So if you now say ADM, if you take that thing and you say like space-time metric tensor, as opposed to spatial metric tensor, it will give you the symbolic metric tensor object, which you can then say matrix representation of. So it's pretty easy if you put that in matrix form, by the way, just for visual purposes. But yeah, so you can see if you look at the 3x3 submatrix, apart from the first and second, first row, first column, that 3x3 submatrix is just that's the geometry of the initial Schwarzschild hypersurface. That's just a spherically symmetric 3 geometry.
Right. And these other things you have to solve for.
Exactly. So those are then the gauge variables: alpha, beta 1, beta 2, beta 3. Those are your lapse and shift.
I see. But so in actuality, given that initial data that you've got there is a solution that is just the full four-dimensional Schwarzschild solution.
Yes, and so although this function isn't in the function repository yet, it is in the GitHub repository. And so maybe when we switch over later, I can show you. So that we have functions for solving the ADM equations in generality, and so there's a fairly easy way that you can sort of starting from just this initial hypersurface version, you can reconstruct the analytical form of the Schwarzschild metric from that, just by figuring out what constraint, what conditions need to hold in order for the constraint equations to be satisfied, and so on.
And that's the only solution. Yeah, the four-dimensional Schwarzschild is the only solution given that initial data. Statement or not?
Modulo some notion of equivalence. So you still remember you still have a lot of coordinate freedom. You still have a lot of gauge freedom. There are many ways you can slice up the Schwarzschild geometry, and so it won't always lead you to exactly the same form of the metric tensor as you would get in the analytical version.
Right. So you're saying there are different foliations corresponding to different, which will give you different analytical forms for the four-dimensional metric tensor, because essentially the time coordinate is, the relationship of the time coordinate. Well, I'm not quite sure. Given that you define the space-like hypersurface, the initial space-like hypersurface, subsequent space-like hypersurfaces could be progressively tipped relative to that one.
Right.
Effectively defining different notions of simultaneity.
So the alpha function there is telling you what's the time-like distance between the neighboring space-like hypersurfaces. And the beta 1, beta 2, beta 3 is telling you effectively how do I relabel the spatial coordinates between the different hypersurfaces.
Okay.
And then if you go back to the ADM decomposition documentation, in the full list of properties, you'll see we have support for a bunch of inbuilt gauge conditions. which effectively correspond to different foliation choices. So, okay, those are the initial data. But in here, so yeah, things like, so maximal slicing condition, harmonic slicing condition, 1+ log slicing condition, etc. Those are all different conditions you can put on the lapse function that tell you how you foliate the space-time. And then things like normal coordinate conditions or harmonic coordinate conditions. Those are conditions on the shift vector that tell you how you relabel the spatial coordinates.
Okay, great. All right, let's dive below space, so to speak, and understand how we can the things you've done for building these out of hypergraphs and so on.
Right. Okay. So for that, you'll want the function discrete hypersurface decomposition. And again, there are, as with any of these, there are more in the pipeline that will be in WFR soon. A discrete hypersurface decomposition.
Yeah, I know.
Oh, sorry.
I'm hoping that the search system will.
We only have one function with hypersurface in its description.
Wow, cool. Okay.
So what this thing does is you give it a symbolic metric tensor, and it will do a space-time foliation of it, and it will produce a sequence of hypergraphs that correspond to different slices in that foliation.
Where those hypergraphs are not necessarily related by hypergraph rewriting.
So in the case where you are solving for the thing, numerically, they will be related. So essentially, what we're doing is, it's all right. The key insight is that sort of generalized adaptive mesh refinement is really just hypergraph rewriting with a very weird event selection function, right? Your event selection function is saying progressively refine or coarsen the hypergraph at these points based on some criterion that has to do with, curvature tensors and whatever. And so internally, or formally, you can think of that as being a hypergraph rewriting system just with a slightly odd event selection function.
Let me understand that for a second. So you've got an initial, essentially, triangulation of space.
Yeah, it's not a triangle. It's less topologically structured than a triangulation. But
can we see what the initial one would look like here?
Yeah. So, okay. So if you take, all right. So that particular ADM metric, that's underdetermined, right? That has alphas, betas, and things.
Yeah.
But
No,
if you take Schwarzschild.
Okay. With those symbolic parameters.
Well, those are the coordinates. There should be no symbolic parameters if we want a numerical thing.
Okay, fine. Then what does this mean?
So that's saying, okay, that's telling you which part of the geometry you want to decompose. So it's saying time between 0 and 1, radial coordinate between 0 and 4, and the theta coordinate between -π and π. Then we're saying we want 200 vertices and with an initial sort of refinement scale of 1.5.
Okay. So how do I get just the initial refinement, not the t = 0 refinement?
So I believe, hang on, let me just quickly double check the right way to do this. Sorry, it's I believe you can just put in a time value into the property, but I just want to double check that. One sec.
Okay, but basically what this is, hopefully we'll get some visualization in a moment.
Okay, so all right, so okay, if you were to take that and just say, what would you want? You want polar graph evolution colored.
Polar graph evolution colored.
Yes. So polar graph colored will show you the final hypersurface only. Polar graph evolution will show you all the hypersurfaces, including both the initial and final forms. Right now, there isn't an option, a straightforward option to get just the initial one, but maybe I should add that.
Let's just get fewer of them, and then we can then we'll pull out the initial one.
Right. There we go.
Let's get fewer of them and just get the initial one.
So if you give it if in that property, if you give it a list rather than saying polar graph evolution colored, you say the list polar graph evolution colored, comma, however many steps you want to go. If you say 0, you would just get the initial, I think.
Okay, fine. List or just the 0 there?
No, list and then 0.
Why is this taking so long? I mean, isn't it doing 200 steps? I don't need it to do 200 steps.
No, it's not. No. That's doing 200 vertices. Oh. Okay, I'm not sure why that happened, but there we go.
Okay, 200 versus what's the 1.5?
That's the initial refinement level. So if you increase, so you would get a denser, a more densely connected hypergraph for higher values of that.
Higher values.
For higher values.
So what is the actual computation going on here? Is it a bunch of linear algebra? What is it? Is it going to be faster if I run on a machine with a big GPU and so on?
It's a fair, yeah. It's largely linear algebra. Oh, multilinear algebra, I guess.
All right. So this is, I mean, at some level, I should be able to reconstruct. I mean, the traditional picture of the Schwarzschild solution with in a manifold, so to speak. This should limit to the manifold somehow.
Right, and if you say coordinatized polar graph colored or something, then you'll get that. Yeah, you'll get to see that with the vertex coordinates.
And the vertex coordinates here, this is projecting into, I mean, this is a 3D object.
Yeah, so it gets projected onto a plane. You effectively by default, whatever the third coordinate is going to be suppressed. So that is effectively the embedding diagram for that's a discretization of the embedding diagram for the Schwarzschild metric. Okay,
so what's happening? Okay, there's nothing in the inside.
Yeah, so it gets truncated at a point, at a certain, beyond a certain point. So if you were to extend this indefinitely, it would that interior bit would go on forever, because that's where the coordinate singularity is.
Okay, but let me understand this. I mean, why? But in the far field, let's imagine that instead of a Schwarzschild thing here, I was just doing flat space for my metric.
Right.
What would be the name for the flat space? So if I had a flat space metric, I just want to see what this hypergraph decomposer produces.
You'd want Minkowski.
Okay. So here, instead of this, I want to use Minkowski.
Yeah. You may get some. I'm actually curious. You may get some weird division by zero error. I don't really know.
Been getting. So I just say Minkowski here.
Yes.
And then what for these parameters?
You probably want X, Y, Z or something. T X
parameters.
No, 4. I mean, I'm just saying that the RA1, A2 doesn't make sense. T should be the first.
Okay, so now I want to do the same thing here. I don't know whether I want that A. What do I want to do with the T, R, X? I want to say
so T01 is fine. You probably want X between, I don't know, -2 and 2 or something, Y between -2 and 2. And then you don't want polar graph, you want Cartesian graph to indicate that you're using a Cartesian coordinate system.
That's a big graph. Go down.
I mean that you may want. Oh, you may want to reduce the 2.5, make that 1 or something. Well, I don't know. That may be the problem.
Okay. So why are there 2 holes here?
I suspect that's a discretization artifact. If you run it again, those should not be there. I mean, or there may be holes, but there'll be different holes.
Okay. So then what I want to understand is this thing here. If I look at flat space, okay, fine. So it's some weird thing there.
Yeah. Because remember, the discretization process is fundamentally random, right? We're doing a Poisson It's a Poisson point process.
So we're making, okay, fine. Okay, so here, if I look at the geodesic balls around these points, I would confirm that this is indeed flat Minkowski space.
Indeed, yeah.
But I mean, this is pretty messy. Can I re-render this as to say, how would I re-render this? Can I just
do you want it to be coordinatized? It doesn't have to be coordinatized, right?
Well, let me for now make it coordinatized.
Okay.
But
So
let's make it not tubular, and let's just see what's going on. Let's make graph edge style arrow like gray or something. It's gonna do exactly. Oops, why didn't that work?
it's a list. Sorry.
Okay, it ignored my edge style. I'm trying to understand. I'm trying to see what this looks like, because I'm trying to see. This looks much more densely connected. Okay, let's not.
But it's only densely connected because you made it that way, so to speak, right? If you lower the one, it will be less so.
Okay, so this purports to be flat space, even though this rendering doesn't make it look terribly flat.
Right.
Well, it's flat in 2 dimensions, but I don't know whether that's the right thing, is it? Should be flat
Well,
in
yes,
3 dimensions.
these are meant to be 2-dimensional projections of the hypersurfaces.
Okay, but I mean, this is kind of the null experiment. This is flat space-time,
Right.
supposedly. And so if I were to evolve flat space-time, it should not change.
Mm-hmm. Right.
But yet, if I evolve the hypergraph corresponding to something which is non-flat, I expect evolution of some kind.
Right. I mean, you'll still get quote unquote evolution in the flat space case, right? It's just that, it'll be
change the flatness.
Ergodic enough that, yeah.
Okay, but so in the case of the black hole solution, the single Schwarzschild solution,
Yep.
what I expect again in the evolution is that it will preserve that coarse-grained Schwarzschild solution. Is that true?
That's true. Yeah.
Does it work?
Yeah. I mean, you see that above, right? Like the graphs, they flap around a bit, but the coarse properties are. I think you did a brief evolution. Yeah, there.
Yeah, there. Okay, but so what's a non-stationary solution? What's a non-stationary initial condition? 2 black holes.
2 black holes, yeah, we can do, but that's complicated. FLRW with a dynamical scale factor would be a simple example of a non-stationary thing. Although that's a bit boring because it's sort of conformally flat. Like it's not very exciting to look at.
What does it mean in these pictures that it's conformally flat?
I mean, it will just look like flat space but growing.
I see.
Basically.
Okay. All right. So, and what you found is that for quite a wide class of hypergraph rewritings, you get things that's coarse-grained correctly.
As long as you impose the right event selection function, right? And that's really where, I mean, in a sense, that's where we cheat, so to speak.
But the event selection function is defining foliations or what?
Yeah, exactly. And so we choose. There's enough freedom in how we select the events that we can just say, well, coarsen and refine the hypergraph. In other words, apply the hypergraph rewriting rules in accordance with, where the high regions of high or low curvature are.
But is there not something? Wait a minute. The sort of naturally occurring event selection function, if we were to make essentially a token event graph out of this,
yeah,
would involve more events in places where there are, in a sense, a higher density of vertices, wouldn't it?
Yes, and so in the continuum limit, that would correspond to normal coordinate conditions and geodesic slicing. And the problem with that is that that will stretch in any spacetime where there's a singularity, like or multiple, like with Schwarzschild. It will mean that your foliation, the slices of your foliation will get hugely stretched around those singularities, and so it's not a particularly good gauge choice.
So, and the reason for that is it's like the fact that the black hole never actually forms to the outside observer or something. The time is infinitely stretched. That's
yeah, and very concretely, it means that the vast majority of your rewrites, in fact, in the limit, 100% of your rewrites are going to be concentrated around the event horizon.
Walk me through that. So that's because that's the intuition behind that. The rewrites.
So because that's just where you have the highest density of hypergraph edges, right?
No, I realize that, but I mean, in terms of understanding time dilation, in terms of rewrites.
Yeah.
Right. So what's actually happening? So
that's corresponding to the statement that an observer would. So the number of rewrites you would need to cross the event horizon would be infinite. In other words, it's sort of.
And the interpretation of that is that to an outside observer, it takes an infinite time for something to cross the event horizon.
Yeah, precisely.
But why isn't there a co-moving? Why is what matters? I see. It's because you're pinning somehow to asymptotic infinity. You're making some. Well, explain this. Is that because?
Right. I mean, no. So if you did this in a different coordinate, if you didn't do it in Schwarzschild coordinates, then that wouldn't be. Then you're seeing the hypergraph evolution as observed by an infalling observer in Eddington-Finkelstein coordinates or something. Then it's different. Then nothing special happens at the event horizon. You don't see a sudden spike in hypergraph rewrites there.
I see. So the passage of more time the perceived passage of more time is the doing of more hypergraph rewrites.
Right.
How should we understand the fact that, let's see, the number of rewrites, there is an intrinsic number of rewrites that happen, but to different observers, they can bunch up the foliations or spread them out in such a way that they change the number of rewrites that happen per moment of foliation time. Is that a fair way to say it?
Yeah, I think so. I mean, so the important point is that with any of these spacetimes, the causal graph extends indefinitely. And so you can slice it apart in ways that take, infinite time to reach certain parts, or, infinite numbers of slices to reach certain parts, or you can slice it apart in ways that take finite amount of time to reach certain parts. But in so doing, you're producing essentially infinite, causal edge distances between those slices.
Can we generate the causal graph for this evolution?
Yes, but unfortunately, that functionality is not yet in the function repository. That's in the pipeline.
But so that causal graph, what you're saying is these different coordinate systems sample the same causal graph. It is the same causal graph in the end, but they're sampling it differently.
Right. Exactly. And so the sort of the default event selection function, which is, as I say, the geodesic slicing normal coordinate conditions case for ADM, is essentially the one where, if you like, we have, all the slices are just distance one away from each other in some sense, right?
Yeah.
And so inevitably, that's not going to reach the parts of the causal graph that are infinitely far away. It's not going to reach that it's not going to reach those in finite time.
But the parts of the causal graph, I mean, to a photon, it's just tooling along in some sense, the causal graph, with no time passing. So a photon, if I'm not mistaken, so a photon can successfully reach these distant parts of the causal graph.
Yeah, as can a massive object, right? But the point is that the coordinate system, and therefore the gauge choice, and therefore the foliation observed by those things, is not going to be the default distance one foliation.
Yeah, I get it. But so to an observer, let me think about this for a second. So different relativistic observers. I mean, I'm kind of wondering about mini observers that are based on actually doing rewriting for the observer. Does that make any sense? So in other words, rather than from the outside saying, here's how I slice the causal graph, the observer is seeing these slices.
Yeah.
Asking the question, could there actually be a little critter sort of being updated inside the where you identify a piece of causal graph as this is the observer?
Right. No, I mean, I think we should absolutely do that because, you know, it's useful for physics project purposes and other things. The reason that's not supported yet, at least from my perspective, is that so there's a pretty well-defined way of specifying, you know, continuum gauge choices and then discretizing them. We don't yet really have a systematic way of specifying discrete gauge choices without just kind of straight up, you know, giving the antichains in the causal graph.
I know that this has been the long-running 3+ year story of kind of how do you label, you know, it's depth first, it's breadth first. What are the reasonable choices of orderings?
Right.
Nick, I think if Nick is still with us here, I think you've thought about this a bit. I lost Nick.
Nick is ostensibly here.
Okay.
But
I think this is an old chestnut problem.
Yeah.
Of what are the observer reasonable choices of foliations?
Right. I mean, one question is how much inspiration can we take from the ADM case? You know, like, so in other words, how general are those coordinate systems or are those gauge choices? Like, does it make sense to use harmonic slicing?
No, that's very technical ADM stuff. Let me look at that list. Let's see. We had. Okay, this is hypersurface. Okay, but by the way, when you're showing these, are these generated from hypergraph updates, or are these generated from just taking slices of the Einstein equation solutions?
The first is generated from taking an initial slice. The latter are generated by hypergraph updates. Okay.
And do we know which hypergraph updating scheme is the best at leading to a successful coarse-grained, you know,
because as I say, the scheme is determined entirely by the curvature tensors, right? So essentially, all we're doing is we're saying we've got some very simple set of rewrites that we can apply that coarsen and refine the hypergraph. We compute the curvature at every point, at every vertex, and if the curvature is higher than some value, we apply a refinement there. If it's lower than some value, we apply a coarsening there.
Okay.
So it's a because the purpose of this was essentially to do practical GR. It's a complete kind of backwards hack, if you see what I mean.
Right. So you compute curvature, but do you compute curvature intrinsically using hypergraph methods?
So if there's no analytical form of the curvature tensor, yes.
And do you get reasonable results in that case? I mean, like if you compare it with the case where there is an analytical form.
Yes. Like, yeah. And yeah. I mean, we already showed numerically that the output of functions like Wolfram-Ricci curvature tensor, which is sort of the analog of Ricci tensor for the discrete case, that you get convergence to the right answer. And at some point, I would quite like to write a kind of. I probably should do this with a student or something. Write a systematic exploration of the sort of convergence and stability properties of these discrete estimators.
Right, but this is convergence. I mean, the question of how well they converge is going to depend on the measure in the space of hypergraphs, because there will be hypergraphs on which there'll probably be crummy convergence. The question is whether the naturally generated hypergraphs generated by hypergraph rewriting have, am I not right? I mean, you can probably make a pathological, it will be interesting to see, is there a pathological hypergraph on which, in fact, this will be a good summer school project, are there pathological hypergraphs on which there is ultimately convergence, but it's really slow and silly?
Yeah, I agree. It's testing the limits of how stable GR is in discrete spacetime systems.
Right, but, which is similar to looking at the continuum limit of fluid dynamics or something like that, and saying that there exist configurations of molecules such that the total density is correct and so on, but yet they're not, with reasonable coarse graining procedures, they look wrong.
Right, but in some sense, okay. So one way of interpreting the GR derivation if you don't want to sort of assume weak ergodicity of hypergraph rewriting, which of course we have to assume, another way to interpret that theorem is to say, well, what it's actually saying is, if you consider only causal invariant rewrites that preserve dimension, preserve continuum dimension, then the class of rewrites that satisfy the Einstein equations is entropically dominant in that space, if that makes sense.
Sure. Right.
But of course, there'll be pathological example. Just because it's entropically dominant doesn't mean that it's measure. It's measure one, right?
Okay, but there are multiple things flapping around here. I mean, one thing is the existence of a continuum limit, aka the analog of the second law of thermodynamics for space-time. That's one thing. I mean, basically the statement that everything's going to be sort of reasonable is like a statement of the second law of thermodynamics for the structure of space-time, I believe.
Sure.
And an interesting question is, if we want to see through that to actually see the discrete structure of space-time, because in a sense, what to the numerical scheme is a pathology, to the Brownian motion of space-time searcher is a success.
Absolutely.
So the question would be, where are the most likely deviations? We have talked about this a bit before. Where are the most likely deviations from the continuum limit, aka second law of thermodynamics, aka randomness, ergodicity, whatever, all of these similar concepts? Where is there the most pathology, so to speak?
So my view is, I don't know that it's the most, but I think one place that's quite fruitful to look is cases where there's topology change in the space-like hypersurfaces.
Yeah.
So a very basic example of that is in the collapse of a rotating fluid distribution or something. So you've got some spinning fluid that's described by the Weil-Lewis-Papapetru metric. It then undergoes gravitational collapse, and it limits to extremal Kerr. But Weil-Lewis-Papapetru and extremal Kerr have different spatial topologies, and so there's some, in the continuum case, there's some quasi-stationary transition between them. And so because they have different topologies and their Weil tensors have different forms, there's a sort of there's a relaxation time that's inherent there, where and that's where you see emission of gravitational waves.
Let me understand the different topologies. What are those different topologies?
So a basic one is that with extremal Kerr, you have these two horizons, right? You have the interior and exterior horizons. With Weil-Lewis-Papapetru, there's only one sort of defined surface. But
now, maybe Jose wants to comment on this. I mean, I think Jonathan, you and I talked about this a couple of months ago as well. Mm-hmm. To what extent is this just like a bifurcation phenomenon, where there was a catastrophe theory-like phenomenon of one of these kind of things where there was an initial sort of singularity and then it split in two? Is that, Jose, do you know about this case?
Not much, to be honest. No.
Okay. So Jonathan, I think we talked about it before, and we had some decent physical interpretation of what's going on at this place where there's this splitting into the two, the inner and outer event horizon.
Right.
What was the physical interpretation that we had of that? I've now forgotten.
I can't remember either. I think you were the one who came up with it. So.
Okay, well, that sounds like my kind of thing, but I unfortunately don't remember.
But anyways, my argument is only that what we see in the initial numerical simulations of that is that so the frequency for things like the frequency of the gravitational radiation that gets emitted in that case depends on the discretization scale of the space-time. And so it's possible that we might be able to see some, there might be some observable discrepancy between the continuum and discrete cases.
Wait, what determines the frequency? I don't understand that statement. I mean,
so
you're saying this gravitational radiation emitted at the transition point between the 1 and 2 discontinuities?
During the relaxation phase, right? So anytime you transition between spacetimes with different topologies and crucially with different forms of the Weil tensor. So that includes, say, spinning gravitational collapse, but it also includes, like, if you have two black holes and they collide, right? You've gone from having two punctures to having one puncture, and the Weyl tensors are different. So in that case, because you're transitioning between two different forms of the Weyl tensor, there's a sort of finite relaxation time. In the black hole collision case, that's the ring down phase.
But hold on, with respect to the Weyl tensor and so on, is this not? There's some integral of the surface integral of the Weyl tensor. That, I mean, is this one of these counting things, or essentially a topological counting thing, like, I don't know, Chern classes or any of these other things where you're evaluating some integral over some region, and
yes,
depending on how many holes there are, you get a different number.
Pretty much, yeah. And we actually, the framework supports that. You can, if you take some metric tensor object and you compute its Riemann tensor, which you can do with the function repository, then there's functionality for computing not just, you can compute its Chern-Pontryagin scalar, you can compute its Euler scalar, and so on. And if you integrate those things, then you get things like, the second Chern number, you get the instanton number, you get the Euler characteristic.
Okay, but let me understand this. So you're saying you've put the Weyl tensor, you compute the Weyl tensor, and how should I understand this? What's a simple analog of this? I mean, if I'm going from a simple homotopy type thing where I have something which, like the kind of the pair of pants type situation where you have a cylinder and it breaks into two cylinders.
Right.
What's an example of a thing like what you're describing, where you compute an integral of a local quantity, and then you see that somehow change as a result of a change of the overall topology?
Well, if you take that exact example, if you take the cobordism, the pants cobordism example, and you were to compute the Euler characteristic of those, of that overall space, which you get by taking the Euler scalar and you just integrate it over the boundary, then you'd see a sudden transition from that being whatever 2 to 1 or something, or there's some discrete transition that you would see.
Okay, and the claim is that the gravitational waves are associated with some, in gravitational waves, what you're seeing is Weyl tensor stuff. Is that correct?
Yes, and so for something like a black hole collision, I mean, for an inspire, at least, there are two different sources of gravitational radiation, right? There's the gravitational radiation from the inspiral itself. It's produced by the quadrupole moment of the black holes. Yep. But you also get a second source of gravitational radiation that is from the merging, and that's the ring down, and that's effectively, as I say, the sort of the relaxation of the Weyl tensor.
Okay. So what are you saying here? So you're saying that
that relaxation, like the gravitational radiation that gets emitted during that relaxation, seems to depend on the value that you picked here, like, whether it was 2.5 or 1.5, essentially the underlying discretization scale of the space-time, that seems to determine some shift in the frequency. That seems to induce a shift in the frequency of the emitted gravitational radiation.
Let's just try to understand that. So, and what is the relationship? If I look at the discretization scale and I look at the frequencies, is it that there is, I mean, what you would naively expect is that there's a cutoff in the frequencies that is, that's on the order of the discretization scale, which is absurdly small. And therefore,
right. I mean, so there is a 1 over the discretization scale, to the power 3 or something cutoff. But you also get what you seem to get is some kind of 1 over scale squared shift in the frequency.
Shift.
I mean, rescaling of you see a pitch shift effectively.
Okay, why is that?
I'm not sure that I have a good physical explanation.
Let's figure it out. I mean, so what's happening, I mean, in this cobordism thinking thing, where you go from the 2 legs to the 1 trunk, so to speak, in the merger, you're saying the gravitational waves, you're saying that that very merging produces gravitational waves because the far field Weil tensor has to change as a result of that merge. Is that correct?
Right, exactly.
And I mean, it's like the classic reason for radiation, which is you've got a near field thing, like the classic reason that an accelerated charge radiates is because you've got this kind of hedgehog of field lines for the charge sitting in one place, and there's a different hedgehog of shouldn't call it hedgehog. I mean the sort of outward radial lines from another place. The radial lines have shifted, but at infinity, you can see that there's a difference between the radial lines from position 1 and position 2. And that's something where you have to somehow transition from being the radial lines at position 1 to radial lines at position 2, and that means you have to have a wave go out to achieve that.
Right.
And I think what you're saying is the same thing is somehow true here, that the far field Weil tensor is different for the single black hole as compared to the two black holes, and somehow to represent that transition, there has to be a gravitational wave that goes out. Okay, and now you're claiming that the frequency of that gravitational wave, so in the case of the charges, just you go from here to there, it's just a single sort of update. There's no wave, there's no frequency.
Right.
In the case of ring down, what makes there be something periodic as opposed to just seeing a burst of gravitational radiation?
So my intuition has always been that it's because it's a quadrupole moment, right? It's because it's kind of wobbling in two different axes.
But that's not for the ring down phase. That's for the general in-spiral phase.
But even during ring down, you see. I mean, I don't know. Jose probably has a better intuition for this than I do.
Is Jose with us?
Yes.
Can you save us from this maelstrom of gravitational radiation? Yeah.
Okay. So to summarize, I think this is a bit like a bell. We have a black hole that has been formed. It's not in its final state, and it has to get rid of excess of various things that in order to relax to the final curve black hole, say. And these excess things will be emitted in the form of gravitational radiation. And it's a bit like a bell. Depending on the black hole that we have formed, these things will be emitted with different frequencies. It has its own, I mean, depending on the mass of the black hole, we will have various frequencies.
Right, but so Jonathan's making the claim that there's a pitch shift associated with discretization.
I can believe that. I mean, if we have a different structure of the space-time at very small scale, that will affect probably the high frequencies part of the gravitational
but only
radiation.
Absurdly high frequencies. But look, in the bell analogy, what presumably affects the frequency of the ring down of the bell is the Young's modulus and so on of the bell. That is how deformable the bell is. So the question is, what's the Young's modulus of space-time?
Well, sometimes the black hole is compared to some elastic surface, and so we have this surface that is trying to get rid of
like a bell.
Exactly, like I mean, if it's not exactly axisymmetric or not exactly spherical for spatial, it would try to get rid of those bumps.
Right, exactly. But that means that there's a question. What is the Young's modulus of space-time?
Or I guess more broadly, what is the equation of state for space-time?
Well, this will be related to the surface gravity of the black hole. So in the end, we only have one parameter, right? Or two. It's the final parameters of the black hole that is going to be
Well, actually, but the critical point is that in our model, we have another parameter, which is the elementary length. See, so any dimensional analysis that you do is going to be blown up by the fact that there's a new quantity involved.
It's important to mention, by the way, actually, at least in the preliminary numerical simulations I've done, you see two effects. One is you see the frequency shift at the high frequency, the high energy end. You also see that the ring down phase occurs earlier than it sort of should, so to speak, if you assume the continuum approximation. Simply because the higher the discretization scale, the sooner the transition happens between either the in-spiral phase and the ring down phase, or the collapse phase and the ring down phase.
Well, basically, the point that you're making there is to know that you have a single black hole. If there is a coarser discretization, the black hole becomes a single one more quickly than if there's a finer discretization.
Right,
You
exactly.
can't distinguish two black holes if they're smaller than if they're distinguished by something smaller than the discretization scale.
Right, right, and so you see, yeah, there are two. If you do the simulations, there are two discrepancies two isolatable discrepancies that you see between the discrete spacetime case and the continuum spacetime case. One is sorry.
Did you have a plot of the? I mean, you had some kind of plot of this.
I did, but it's very old now, and I want to do a follow up that looks specifically at that problem.
Do we need to blast it with lots of computer time?
I mean, that would always help. I ran it on I have access to university supercomputer clusters and things, so that I can do that. But if we can do better somehow, then
right. Well, I mean, okay, but yeah, we're running out of time here. But the basic point is, I think I understand how these simulations work, and the key thing, and our best hope seems to be, some sign of what's going on based on gravitational radiation at infinity. That seems to be about the only. And I think before we were talking about gaps between optical phenomena and gravitational wave phenomena. I'm not sure.
Right. I mean, so one possibility, it remains a speculative possibility, is that we have some idea of how photon propagation works in a discrete spacetime. We have some idea of how gravitational waves work, but neither is complete yet. But it's at least possible that in these kind of multi-messenger astrophysics scenarios, where you have people looking for both, say, neutrino signatures and gravitational wave signatures, or electromagnetic signatures and gravitational wave signatures, that there could be observable discrepancies in the arrival times of those different messages.
Well, let's understand why. I mean, the point is, a photon what's the difference between, well, I mean, one would normally think all the action is happening at some kind of event horizon, or near some kind of event horizon, both whatever optical phenomenon there is of matter being accelerated to some ridiculous rate and radiating, and gravitational waves being emitted. It's all, in the end, they appear to be being emitted from the event horizon.
Right. Right.
But I mean, one huge difference in our models is that we do have an internal model for the black hole. We don't just say, oh, it's an event horizon and we can't say what's happening inside. We only have an exterior solution. We have an interior. We have a full, am I correct in saying that? I mean, that we in a sense have a full solution for the complete structure of the space-time, even inside the black hole.
Yeah, if you take a sort of, I mean, again, to stress, these are sort of very synthetic hypergraph writing systems that have been engineered to mirror certain space-time geometries. If you take a sort of homegrown hypergraph writing system, though, that contains a Schwarzschild black hole, then yes, that will, or that contains a black hole, then that will be the case. There won't be some, arbitrary cutoff point where you can't talk about it anymore.
Right. So one of the questions is our kind of event horizon porous in a way that one in continuum space-time would not be? And if that's the case, is it possible to effectively get gravitational radiation, if not photons? I can imagine a situation where you can't fit a photon through, but you can fit something that essentially forms itself into gravitational radiation. So what's an example? To take an extreme example, you've got a harbor with a bunch of water, and you've got water waves, and they're flapping around on the surface of the water. And you've got a boat, and you could easily imagine a situation in which you can't fit the boat through some hole in the harbor wall, but you perfectly well can get these. I mean, there's a bad example because we really need something where the intrinsic structure of the thing is defined by the water, as opposed
to. But I get your point. I mean, like, or maybe one way to say it would be that sort of gravitons in inverted commas in this model, by which I just mean the carriers of gravitational information are just causal edges / events, right? There is no. Whereas photons probably, whatever they are,
big fluffy things,
likely have some internal structure. And so, unlike most quantum gravity models, there probably is some large size discrepancy between the photon and the graviton.
Right. Or a minimal graviton is
right.
I mean, what aggregates to something that is a full sort of particle-like propagating graviton. Yeah, I mean, right. There's a core to the photon that defines its quantum numbers and so on, that requires a bunch of causal edges, whereas gravitational effects happen even down at the level of a single causal edge.
Right. And so therefore there are presumably obstructions that will apply to photons but won't apply to gravitons.
Right. In particular, the shredding of space-time. There can be a situation in which gravitational effects can propagate through, but photons cannot. And it kind of reminds me of these cyclic universe things, where which have that feature, don't they? That the gravitational waves can get through the crunch, but other things cannot.
I think so. Yeah. Certainly in like, I don't know. I've heard Penrose claim that in CCC you can, you can see gravitational wave signatures from prior eons somehow. I don't.
Well, it's probably the same phenomenon as we're talking about here,
mm-hmm.
Except that because any well, all right, this is exciting. We got further to go here. We're going to find, it's super embarrassing as in Brownian motion was discovered 100 years before people understood it was due to the presence of molecules. And I think we've discussed previously that it's quite possible that there's an astrophysical phenomenon sitting out there that's been around for a really long time that reveals the discreteness of space-time, and we just don't know it yet. Right. And obviously the best candidate for that will be dark matter. And perhaps we should discuss a different time the use of these simulations to ask questions. I mean, what would it take in this kind of simulation strategy? We're dealing with the extreme case of black holes. What would it take to get not such an extreme case, but rather just a standard, big black hole at the center of a galaxy rotation curve type thing?
Well, for something like, you'd probably still want to use Schwarzschild or something like, like Schwarzschild is a good metric even for non-black hole cases, right? Just for massive objects.
The rotation curve of a galaxy, we could just look at orbits in the Schwarzschild solution.
Right, and I don't know a huge amount about galactic astronomy, but my understanding is that's a pretty good approximation. Like the galactic cores are often sufficiently slowly rotating that Schwarzschild is a good approximation.
Oh yeah, I'm sure, but there's also a bunch of there's only 10 to the 5 solar masses right at the center of our galaxy, but there's on the order of 10 to the 11 solar masses in the whole galaxy. Our galaxy has not all ended up in the garbage can yet.
Right. But yes, anyway, and there's functionality for doing, it's actually quite nice. There's functions like discrete hypersurface geodesic, which is again in the GitHub repository, but not yet in WFR, which essentially reduce solving the geodesic equation to solving for, graph geodesics in the hypergraphs. And so you see, we can easily.
That's nice. So we can get the orbits.
Yeah, exactly.
But the phenomenon that we're looking for is that there is larger effective gravity associated with the external orbits than you would expect from the matter.
Right.
And the question that we could ask then, we don't really have a great definition of matter. The only definition of matter we have is solve the Einstein equations and see what's there.
Right. Well, in a
Although
sense,
we do have a definition of matter, which has to do with, no, it's not clear, because I mean, dark matter could be as effective in, if we look at the flux of causal edges, that could perfectly well include dark matter.
yeah, I mean, my basic position about this is that dark, okay, as in the true spirit of the equivalence principle, the distinction between what is matter and what is space is not a particular, is not defined a priori, right? That's something which we have we have the freedom to choose. And so, whatever the dark matter story is in the Wolfram model case, my guess is that it's just something about, there's some feature of space that we have chosen to interpret as a matter distribution, but it's really, it's ultimately just some feature of space, right?
Yes, or alternatively put, there's a zero in some kind of normalization, renormalization story. There's a definition of what space is that is slightly off.
Right. But yeah,
Right.
and in a sense, the fact that there's no a priori way of saying this bundle of hyperedges is matter, this bundle of hyperedges is background space, is precisely the statement that, you can switch any positive term in the Einstein tensor to a negative term in the stress energy tensor, and vice versa.
And also our expectation that the vast majority of causal edges are associated with knitting together the structure of space, not with providing the things that we identify as matter.
Right. Yeah. And that makes your questions about, equations of state of space-time and so on quite, I think, quite well defined, even if you don't know how to answer those yet.
Right. All right, time to
on a very mundane level, though. I mean, one of the things I wanted to get out of this was just a sense of, is the interface to all this functionality, with setting up symbolic metric tensors and symbolic tensors and plugging these into discrete hypersurface decomposition stuff. Like, does that interface sort of make sense?
More or less, but I have to say, I feel like this whole thing is very much at the research phase, and the uses are going to be leading edge research kinds of things rather than sort of industrial production type stuff. And so I think that the fact that you might have to read the documentation to figure out what's going on is probably less important.
Fair enough. I mean, my hope would be that at least the symbolic side, like at least the non-numerical side, might be useful, just as we've seen with the quantum framework being used in teaching and stuff, that it might potentially be useful.
I agree. I mean, this clarifies a lot of things about how things work I think this needs another iteration for that. But
right.
I think that I mean, these things always, even my own little understanding of ADM and things like this is greatly helped by sort of concretizing these things in terms of functions and so on. And I think other people's will be too. Being able to see that, being able to see what it means. Asking questions like, what does energy mean in in general relativity? We could probably compute that from all these things explicitly and see that, there's an unknown zero and et cetera, et cetera, et cetera. Right. Which seems useful. Right. I have got to go actually to another live stream, but this was a fine discussion and to be continued. And let's go find Brownian motion in space-time. But I think we still got a few more iterations to go. I think we should talk about this thing about GD6 orbits defined by GD6 and how that relates to what is merely knitting together the structure of space versus, really what we want is something where there's some kind of overrun from knitting together the structure of space. It's something kind of not like gravitational magnetism. It's some, what I bet it is? I bet there's something like viscosity in space-time. Just like you can get, or some effect that goes beyond. In other words, what the question is the identifiable mass in the galaxy all leads to gravity.
I mean, the presence of viscosity should be fairly easy to test, right? Because all we have to do is check whether the continuum equations that describe the propagation of gravitational radiation, whether they are purely hyperbolic as they are in the continuum case, in the normal continuum case, or whether they have a parabolic damping.
Yeah, okay. So there isn't ordinary viscosity because that would actually damp out gravitational waves.
Right. Yeah, you'd see gravitational wave dispersion, which I don't think is observed.
No, it is not. I mean, so far as well, at least actually you just see damping. It depends on whether it's bulk viscosity, shear viscosity, what the kinds of, and gravitational waves anyway are differently classified because they're neither long, they have quadrupole deformations, et cetera, et cetera, et cetera. All right, I better go to my other thing, but let's continue this hopefully sooner rather than later, because this was fun and exciting, and I think we're getting somewhere.
Sounds good. Thanks.
All right, thanks to folks on the live stream. Thank you, Jonathan, Jose, et cetera. See you all soon. Bye for now.